Alright, so hopefully you watched the demonstration video already, so you have an understanding of what a standing wave actually in motion looks like. So remember, a standing wave is when two waves combine according to the superposition principle. And at the right frequency, the wave will appear to stand still. So essentially you have the wave and then its reflection adding together so that you get constructive interference or total destructive interference. So it looks like a transverse wave that is standing still, and you would have seen in the high-speed camera that it really is actually in motion. It's just how our eyes perceive it. So I'm going to introduce some vocabulary words. Here we have an antinode, and an antinode occurs when you have constructive interference, and a node appears when you have total destructive interference, so that when the amplitude of the two waves add together, they add together to get zero. The distance between nodes is half of a wavelength, so between here and here is half of a wavelength, and the distance between a node and an antinode is 1/4 of a wavelength, so between here and here is 1/4 of a wavelength. And we want to be able to create a relationship so that we can calculate what the frequencies are that lead to standing waves. And as the gentleman would have said in the video, the frequencies are going to be in integer multiples of what we call the fundamental frequency. Alright, so let's drive that relationship. So we're going to start with the idea that frequency is equal to speed of the wave divided by the wavelength. And remember earlier I said that the distance between nodes is half of a wavelength. So the distance between the nodes L is going to equal 1/2 times the wavelength. So the length of our string here, that's been fixed here and fixed here, L is going to be half of a wavelength. So I'm going to sub that in. And I'm going to multiply by 2 on both sides so I can solve just for wavelength, which becomes that 2 times L is equal to the wavelength. So here we have a relationship where the frequency is equal to the speed of the wave through the string divided by 2 times the length of the string, or at least the length of the string that is fixed between the two posts there. Let's do the same thing for n equals 2. So we have a node, and a node. So this would be half of a wavelength, this would be half of a wavelength. So in this case, L is just equal to the wavelength because we have two half wavelengths. So we're starting with frequency equals speed over wavelength, and plugging in for wavelength in this case, we have L. Now I don't want to have to draw this picture and drive this every single time I want to figure out what an integer multiple of the fundamental frequency is. So we're going to do a little bit of a math trick here. I'm going to multiply by 1 up here. That doesn't change anything. I'm going to multiply by 2 over 2 here. And 2 over 2 is 1, so I'm just multiplying by 1, so I haven't changed the equation at all. Notice now, though, you have a 2 on the bottom in both cases, and that the integer up top matches what we're going to call the harmonic number. So n equals 1 versus n equals 2. So I can write a master equation here where the frequency that you're going to get a standing wave at is equal to n times the speed of the wave divided by 2 times L, where n, which we're calling the harmonic number, is equal to 1, 2, 3, 4, etc., etc. And if we wanted to, we can rewrite this as the fundamental frequency is equal to the speed divided by 2 times L, and any future frequencies is equal to n times that first frequency, or fundamental frequency. Now I do want to point out here that the speed we've been talking about, the speed of the wave through the string, is something we learned how to calculate at the end of topic 13. So in this case, the speed is equal to the the square root of the tension in the string divided by your linear mass density. And I want to caution you, when you calculate the linear mass density as m divided by L, the two L's are not the same L necessarily. This L here is the length of the entire string, and this here is the length of the string that's actually pinned and is vibrating with the wave. And yes, there can be instances where those are two different numbers. We used to do a lab, and we don't do it anymore because the equipment became old and it was hard to get the equipment started, where we would have essentially a giant tuning fork that we would attach a rope to and hang the rope over the edge of the table so that the one end attached to the tuning fork would be a node and the other end that was pinned to the table would be the other node. But then there was string hanging over the edge of the table with a giant mass attached. And so we had to include the length of the string when calculating the linear mass density, but we'd only use the distance between the tuning fork and the edge of the table when calculating what the frequency should have been. Alright, so now we're going to discuss standing waves and error columns. And I always do the string first because you can visually see the string. It's harder to actually see the wave inside of an error column because we can't see air. Alright, so I've drawn n equal 1 and n equal 2. And the big difference between what we started with and what we're looking at now is that the n equal 1, you go antinode, node, antinode versus what we were doing before, where we were going node, antinode, node. Since we know the distance between an antinode and a node is 1/4 of a wavelength, and we have two of those here, L is once again going to equal half of a wavelength. And for n equal 2, let's see, we have 1, and then a half a wavelength and another force, so that leads me to L equal the wavelength again. So the formula here is going to be the exact same formula that we derived before, where the fundamental frequency is going to equal the speed divided by 2L, and then any future frequencies that produce a standing wave, you're going to get n times that fundamental frequency, where n can equal 1, 2, 3, 4, etc. I do want to point out here, though, that how you get the speed, because we're not traveling in a string anymore, we're traveling through an error column. So this is something like blowing into one end of a clarinet and having the sound come out at the other end. That would be the speed of sound. So unless you're given a different medium or a different temperature, you're going to use that 343 meters per second. Alright, we can also have an error column with one end open. An example of this might be if you filled a glass partially with water and then ran your fingers along the edge, and it produces a sound. And you can actually adjust the frequency at which it produces sound by adjusting the water level in the glass. So I've drawn here n equal 1, and because we're dealing with one end open, I've made one end here closed up, and that's a node. So this would be like where the water level would be like in the glass. So imagine I rotated the glass sideways. And the other end has to be an antinode because it's open. So in this case, because we're going from a node to an antinode, L is equal to 1/4 of a wavelength. Now I've run into a problem where I'm trying to draw n equal 2. Because when I go to draw n equal 2, that would mean that I would need to have a node here and a node here. Because essentially it would be a half of a wavelength. But that's impossible to draw because we have one end closed and one end open, so there has to be an antinode on one end and a node on the other end. So we have to skip to n equal 3, where we can have a node and then another fourth wavelength with a node and then another fourth wavelength with an antinode. So that means we have 3/4 wavelengths is L. Alright, starting with the idea that frequency is equal to velocity over wavelength again, we can say that velocity divided by 4L matches up with n equal 1 or the fundamental frequency, or that frequency equals velocity divided by 4/3 times L, and because we're dividing, it flips our fraction, and we get this relationship here. So it's very obvious here, the idea that we can put a 1 up here, and so this integer up top matches what the harmonic number is, and then instead of having 2L in the bottom, we have 4L in the bottom. So we can say the fundamental frequency is equal to the speed of the wave divided by 4 times L, and that any future harmonics is equal to n times that fundamental frequency. But in this case, n is equal to 1, 3, 5, etc. There's no even harmonics. And once again, because this is through an error column, you're going to use the 343 meters per second for the speed of sound, so the velocity in this equation, unless you're told it's a different medium or a different temperature, in which case you have to figure out what that speed is first.